there, here's the third lecture video of Chapter 4. So we are picking up with our third type of reactions we're talking about. So the third type is going to be acid-base reactions. Remember, we have 5 to get through. You're going to notice that these are really similar to precipitation reactions, and that's because they are another type of double replacement. So remember, double replacement is when you have like AB compound, CD compound, and all they do is flip partners, okay? So that's what happened with precipitation. But what we got with precipitation was we always had 2 aqueous reactants, and we made a solid product, remember? So that's a precipitate. Whereas acid-base reactions, you're going to have an acid and a base, and you're going to neutralize them. So let's talk about what that looks like. So first, let's identify who's an acid, what does it mean a little bit, and same for bases. There's going to be, this will just be a quick overview of each. So acids in general, they're going to produce H+ when dissolved in water. So for us, they're going to start with hydrogen, okay? And remember that you're going to memorize the 7 strong acids. However, you can also identify acids in general if they start with H, and they're weak if they're not on this list, okay? So remember, the weak acids would be, a couple of examples would be HF or HNO2. Those would be weak acids. And just a reminder, strong acids are strong electrolytes. Weak acids are weak electrolytes. That's going to matter here in a little bit, okay? Because remember, strong electrolytes break up into ions, whereas weak electrolytes form some ions, but mostly molecules, okay? They mostly stay intact. Okay, that'll matter in a little bit. Bases, we've also mentioned them a little bit earlier when we saw the strong bases. They all produce the hydroxide ion in solution. There are different definitions of acids and bases. So what I'm referring to here is the Arrhenius definition, and we're just doing a quick overview of recognizing acids and bases. So here are your strong bases to memorize, okay? And once again, I'm going to remind you that they are strong electrolytes, so they break into ions when they're in solution. Because remember, this whole chapter, we're talking about aqueous solutions, so we have to be dissolved in water. So let's see what happens when these two get together. So here you see acid and base together. They are always going to make a salt and water. Salt is just another name for an ionic compound. And it's always going to be an aqueous ionic compound. So it's always going to be soluble if we're working with an acid and base here. Okay, so for example, if you see HCl, if I break that apart for you, H is going to always have a +1 charge when it comes first in an acid, and then Cl-. The way you can remember that for hydrogen is he's in group 1, so he acts a lot like a group 1 metal, okay? So that was not very legible. H+ and Cl-, and then Na+ and OH-. And what's going to happen is they're going to flip-flop, right? So you'll have H and OH come together. That's where your water comes from, right? And then your other two are going to combine, and you're going to do the flip-flop method, and you're going to get NaCl. Okay? This is your salt. This is your water. So here, you'll notice it written out as the molecular, right? Everything's intact. You balance it with coefficients. Complete ionic. Here's the deal. You break apart anything that is aqueous and a strong electrolyte. So you're breaking apart any strong acid and strong base. As long as they are strong, they're coming apart. And then your product is aqueous, so it's coming apart. However, your water is liquid, so you leave it intact together. Does that make sense? And then remember, spectator ions just are boring. They're like me at a sporting event, okay? I mean, I love sports, and I just sit, but I'm not participating. I like to watch the sport, okay? So these guys are the spectator ions. You leave them out, and then you get your net ionic. See how similar it is to before? Now, when you have a weak acid or base, then you have things that are not going to come apart, okay? This is generally going to be a weak acid for you. The bases that you're going to run into are generally going to be strong bases, okay? So like if you look at acetic acid and barium hydroxide, acetic acid, the HC2H3O2 is not strong, so he's weak. Barium hydroxide is strong. So look what we're working with. We are working with a weak acid here and a strong base, okay? Now, it's still going to be neutralization no matter what. So you're going to have acid, base, and try to remember what do you make? A salt and water. The good thing is you don't even have to have that memorized per se because you can determine it. Watch what happens. If you have HC2H3O2, aqueous, plus your barium hydroxide. Okay, so we have a compound and a compound, right? Here, if we break apart, just so we can kind of see what's happening here, we have an H plus and we have acetate. Remember, have your polyatomics handy when you're working on this at first. And then barium plus 2 and hydroxide minus 1. Remember, I'm not concerned at first with how many, just who is the ion and what is his charge. Then you're going to flip-flop, right? So let's see who's going to go with who. H and OH are going to make water, which will be in the liquid form. And barium and acetate will come together. You flippity-flap, and so you get barium and 2 acetates. Do you see where I got that from? The charge is flip-flopped. And he's aqueous. And he always will be if we're putting together an acid and a base here. But if you want to go to solubility rules, it'll further clarify that acetates are soluble, so he's also soluble. Let's see if we need to balance him now. I'm sorry, my color combo here is not looking too good. I don't know what agrees with these. Okay, so you see how we have 1 barium and 1 barium. That looks pretty good. We have 1 acetate here. See how the polyatomic, there's only 1, but there's 2 here. So let's throw a 2 here. So 2 acetates, 2 acetates, 1 barium, 1 barium. Now, 2 hydrogens right here and 2 hydrogens. And then there's an additional 2 oxygens here. So if we have 2 oxygens, you see how we only have 1 here? We're going, I think I misspoke a minute ago, we're going to have to put a 2 here to get 2 oxygen, 2 oxygen. And then see how there's 2 hydrogens here and 2 there, making 4, and 4 hydrogens here. Okay, so now we're balanced. That is our molecular equation, right? It's a lot of work. The molecular, you had to do a lot of thinking. Okay, come up with the charges, flip-flop the charges, balance the equation, okay? Now, for the complete ionic, we're going to have to break it down. It's tedious, but it's not necessarily hard. You've kind of done the hard work. Okay, this guy, however, is he a strong acid? No, he's a weak acid, which means he's a weak electrolyte. So you are going to leave him intact because that's more representative of him. In solution, he stays together more than he breaks apart. This guy is a strong base, though. Remember, strong bases are strong electrolytes, so you're going to break him apart because in solution, this is what he actually looks like. Now, in a complete ionic, you do care about the number of everybody. So you see how you have 1 barium and you have 2 hydroxides. Okay, and then our products, we've got to leave water together because remember, solids, liquids, and gases you leave together. Aqueous you break apart if they're strong electrolytes. This is a strong electrolyte, so we're going to leave barium out alone. And we're going to leave acetate out alone. Uh-oh, how many acetates do I have? I have 2, so I need a big 2 right here. Everybody feel good about that? Okay, that's our complete. Then let's just X out whoever's spectator. I believe it's just barium. So what I'm going to tell you is what's left here is the net ionic. Because all the things that are left are the ones that are actually having some change. So what remains is the net ionic. Okay, and we'll do one more like this. Okay. So now take a minute, you might even want to just pause and try this next one on your own. It's going to be really similar. So you have a weak acid with a strong base. So work through it and try to determine who your products are and then break it down into your ionic ones. Okay, here's what happened with the flippity flap. H and OH came together to make water. K and CO3 came together to make K2CO3. And then I'm going to balance it. 2 Ks, 1 CO3, and we're going to need a 2 here because there's 2 oxygens and 2 oxygens. There's 2 hydrogen and 2 hydrogen to make 4, and 4 hydrogen there. So that is the molecular. Now we'll do the complete ionic. Okay, we break apart anything strong. This guy is a weak acid, so you have to leave him together. This guy's a strong base, so you break him apart. Potassium carbonate is a strong electrolyte. Remember, anything with K plus will break apart. Okay, leave water together because he's a liquid, so that's the complete ionic. And then lastly, we'll keep anything that changed. So let's just identify who did not change. K plus, that's all. So we got to write the whole thing, everybody but him. And there's your net ionic. Okay, so same premise, just be sure that you're leaving together anybody that's a weak electrolyte, which is essentially a weak acid, okay? And you can refer back to the beginning of the notes if you kind of forget who the strongs, the weaks, and the non-electrolytes are, okay? So that was reaction type number 3. Next is going to be number 4, and this will be the gas-forming reactions. So we're going to produce some kind of gas. They're actually going to be very, very specific, okay? It's going to be one of these 3 scenarios, meaning if you're double replacement, you're still double replacement, okay? Where you have A, B, C, D, and you flip-flop. But what you're going to get is one of these 3 products. If you make H2CO3, if you make H2SO3, if you make NH4OH, those 3 compounds are very unstable. They will immediately break into these 2 components, one being a gas. Do you see what I mean? So if you get one of these as a product, they will immediately break down. So you're going to form either CO2 gas, SO2 gas, or NH3, ammonia gas, okay? We really just have to memorize these 3, okay? So watch what happens here. If you have calcium carbonate and HCl, you do the flippity flop. Calcium and chlorine come together, no big deal. Flip flop. H plus and CO3 minus 2 come together. Do you see how that would have given you H2CO3? We would have gotten H2CO3, but ding, 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 it's unstable. So it immediately broke into CO2 gas and liquid water. Okay, so it really comes down to just kind of memorizing these 3. So here's the next scenario, similar thing where you make H2CO3, it broke down into CO2 gas and water. This one instead made H2SO3, sulfurous acid, and you'll see how he broke down into SO2 and water. So just watch for these 3 compounds to be formed in your metathesis or double replacement reactions, okay? Now let's talk about how to write a net ionic for them. That's really maybe the only additional thing to talk about. Remember, you leave solids, liquids, gases together. So I'm not going to break apart this guy, and I'm not going to break apart this guy, and I'm not going to break apart that guy, because they stay together. In solution, the aqueous ones are the ones that can break apart if they are strong electrolytes. Do you get what I'm saying now? So you have to be aqueous, and you have to be a strong electrolyte, which means you're either a strong acid, a strong base, or an ionic compound, which we are. This guy is a strong acid, so he'll break apart. This guy is ionic, so he will break apart, and he's soluble with the solubility rules. So here we just break apart the ones we can. So CaCO3 stays together, but H plus and Cl minus. Oops, you know what? This is not balanced. Let's balance it first. So you see how there's 2 chlorines on the right? So let's throw a 2 there for 2 chlorines. 1 calcium, 1 calcium, 1 carbon, 1 carbon, 3 oxygens, 3 oxygens. We're good. So there's going to be 2 H pluses and 2 Cl minus. And then you break apart your calcium chloride, showing their charges. And remember, there are 2 chlorides there, plus CO2 gas, plus liquid water. And that's your complete ionic. And then your net ionic, let's see who we can leave out. Let's go identify the spectator ions. 2 chloride, 2 chloride. Everybody else is tied up, so you're going to end up with CaCO3. Tied up wasn't necessarily the word. What I meant was the rest are changing. Does that make sense? Like calcium was tied up here, but he's not anymore. So there's your net ionic. Okay? All right, and then the last of the type of reaction. Oh, that's not true. I think maybe I've miscounted. Anyhow, that's okay. Displacement. Yeah, the last 2 kind of go together. So what we have talked about so far, just to kind of recap, and let me see if maybe I got my numbers wrong. Maybe I did, yeah. Okay, so precipitation was 1 type, right? Number 2, I labeled incorrectly. Acid bases will be number 2. Remember, both of those were a type of double replacement. Same for gas forming here. So this was just number 3. Now we're on number 4, displacement. And he's going to look a little bit different. Okay, so we have 2 more to go, displacement and oxidation reduction. So here, displacement, here's what's happening, is we no longer have 2 compounds flip-flopping. That was double replacement, which we've seen throughout the chapter so far. Here's what we're calling single displacement, really, where you have a single element and a compound, okay? It's a lot like a middle school situation, like somebody's alone, there's 2 friends here, and then they flip-flop, right? So A replaces or displaces 1 person in the compound. So A and B switch, or A and C switch, right? Someone else gets kicked out and left alone, right? So here, what we end up having happening is ions change charges, okay? They'll go from either a different charge, or they'll go from a solid to a charged atom. We're going to talk about that right down in here. So if we look here, and we'll talk about their charges more as we go. Okay, let's skip this part for just a second, and let's come here. If this displacement occurred, what would we predict, okay? Do you see that right now silver has a 0 charge because he's all by himself? He's a solid metal. Copper and chlorine are together in a compound. Chloride is always -1. If he's -1, do you see that copper will have to be +1? Okay, who can silver displace or replace? Because what charge does silver have the ability to make? If you recall, silver has the ability to make a +1 charge. So he can replace the positive guy. So silver is going to come together with chlorine. They're going to come together, and they're going to be AgCl. And then who gets kicked out? Copper. Now watch what happened with their charges. We'll talk charges in a little bit. But do you see that now silver is a +1? He was 0. Copper was a +1, but now he's 0. Chlorine is still -1. So I'm just paying attention to charges just so that helps us in a little bit. Okay, now what would you expect to happen here? So let's do similar prediction. And then we'll talk about which of these reactions actually occurs. Okay, copper here starts as no charge. Silver's in a compound +1, chlorine -1. Copper can only be positive, so he must replace the positive guy and go together with chlorine. Okay, here we don't have a pulse on what charge copper would take on, because do you remember as a transition metal, they can take on different charges. So like copper sometimes can be +1 and sometimes can be +2. So here I'll give copper a +2 charge, but that wouldn't be fair to expect you to know at the moment which one he would produce. So here now silver's 0, copper's now +2, and chlorine's -1. Okay? Now let's talk about this. So that's just prediction of who will replace who, okay? Now we've got to use this thing called the activity series, okay? So we have activity series. Let me pull this up for a sec real quick. Okay, so here, let's pull up the activity series. And these are found on Moodle on your Chapter 4 handout. So here's solubility rules, and then here we get to this thing called the activity series. You do not have to memorize this. It's something that you could always find if needed, okay, and will be provided on, well, you'll have it handy on a test, right? Okay, what this means is the metals at the top of this list are the most active. Okay, they're the most easily oxidized. We're going to talk about what that word means in a minute. Essentially, they're the ones that are going to end up in the compound. If you want to talk about middle school, just think the higher on here, the more popular. You're going to end up in the group. Does that make sense? It's a terrible example, but maybe it'll help you. The higher you are on this list, the more likely you're going to be in the compound. Remember? So if we look over here, let me see if I can show both at the same time for us. So we can predict whether certain displacement reactions will occur, okay? Like look at silver and look at copper. Okay, let's go find them. You see silver's here and copper's here. You see how I'm comparing the two? Who is the more active metal? Copper is the more active metal, right? So if copper's more active, he's the one that's going to end up in the compound. Do you see in this scenario, he's already in the compound? That means this reaction will not happen, actually. So I know I made us run through it, but just as an example. This one won't happen because copper's already winning. In this reaction, however, copper will replace silver because copper's more active. He is more easily oxidized. He'll take the place of silver and end up in the compound. So yes, this one would occur. Does that make sense? So we have to be able to do two things. We have to be able to predict whether this is going to occur, and then also, if it is, then what will the new compound be? Okay, so let's keep practicing here. Let's look at this guy. Magnesium is above lead in the activity series. So magnesium's here, and lead is way down here. So right off the bat, what does that tell you? Who's going to end up in the compound? Magnesium. Okay, so will this reaction right here happen? Yes, it will happen because magnesium is more easily oxidized. So he's going to take lead's place, right? So right now, magnesium's 0, chlorine's a -1, and Pb is a +2. Okay, when we flip-flop, magnesium and chlorine will come together. So magnesium has a +2 charge, chlorine -1. So flippity-flop there. And then leaving lead all out by himself. Once he's alone, he no longer has a charge. He's 0 now. So those are your two products. And then, of course, if needed, you could balance with coefficients. So now y'all try to stop and think on your own if this will occur. Will an aqueous solution of iron 2 chloride oxidize magnesium metal? Okay, let's not worry about the oxidized word yet. We're going to learn that here in a second. But if we have iron 2 chloride, that's a compound, right? Oxidized magnesium metal. So do you see that he's alone? So let's just decode even if we don't know what this word means yet. Okay, iron and magnesium. You go over here and you compare. Here's magnesium. Here's iron. Who's higher? Magnesium's higher. So what will happen? He will win. So if he will win, he will replace iron. So magnesium's going to go into the compound, you flip-flop the charges, and you leave iron alone. Okay? Any questions there? Okay, and then which of the following metals will be oxidized by PbNO3 Meaning, can zinc take his place? Can copper take his place? Can iron take his place? You're looking for any of these that are stronger, right? So is zinc above lead? Let's see. Here's lead, and zinc is above him. So yes. How about copper? Copper's down here, lead's up here. Lead wins, so not copper, right? And then iron, who's higher? Here's lead, and here's iron. Iron wins, yay. So zinc and iron would react, copper would not. Okay? Now, let's work on this whole thought of oxidation. Okay, this is our fifth and final type of reaction here. Then we turn to a little bit of math at the end of the chapter. These are called oxidation-reduction reactions. They're also called redox, okay, for short. Here's what's happening. Somebody is oxidized and somebody is reduced, okay? And we were actually seeing this happen a minute ago. We just weren't using the words yet. Oxidation means that an atom or ion loses electrons. So oxidation occurs if you lose electrons. A lot of times you use the term Leo the lion goes grr. So what that means is reduction is if you gain electrons. So let me show you. Loss of electrons, oxidation. Gain of electrons, reduction. Do you see that? One person's losing, one person's gaining. Everybody with me so far? One person has to lose, one person has to gain. Otherwise, it won't work, okay? And Leo tells me that the one being oxidized loses electrons. The one being reduced gains electrons, okay? So Leo the lion goes grr. Look at this number line down here to help you for a second. Okay, if you are at 0, you have a 0 charge. If you gain electrons, grr, 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 grr. If you gain electrons and you're reduced, what will happen to your charge? If you gain electrons, you'll go negative, right? You'll go down the number line. If you lose electrons, however, so I think gaining makes more sense because if you gain negatives, you're going to go negative. But if you lose electrons, on the contrary, you're going to go up the number line, right? So an example here that you could write for yourself is like if you're thinking about someone losing electrons, then they have to do what on the number line? Think. And maybe reduction makes more sense first. Like say you're starting at copper +1. If you gain electrons, you go down. So if you gained 1 electron, you would then be just normal copper. Whereas oxidation is if you're copper and you lose an electron, you go up the number line. And we're going to practice this, okay? You lose an electron. So let's come down here and look more at it. And a couple of things here. Why don't we go back up here just for a second and y'all tell me kind of what happened in this scenario. You see how copper was 0 and now he's +2? He was 0, now he's +2. So think on the number line. I always ask myself the question, did he gain electrons? If he gained, he would have gone down negative, but he didn't. He went up. So he didn't gain, he must have lost. So Leo, he was oxidized. So somebody had to be reduced. Who was it? It's silver. Because look, silver was at +1. He went down the number line. If you went down the number line, you must have gained negatives, right? So he was reduced. Now the one extra thing to add here is the question can say, who was oxidized, who was reduced? The question also could ask, who is the oxidizing agent and who is the reducing agent, okay? So what that looks like is the oxidizing agent is the one being reduced, okay? Let me explain this better. If you are being reduced, You're allowing someone else to be oxidized, okay? So up here, let's put it over here. Whoever's being oxidized is called a reducing agent. And let me make sense of that for you one more time. If you are being oxidized, you're allowing someone else to be reduced, which is what an agent does. An agent is not the famous person. The agent is allowing someone to be famous, right? So if you're oxidized, you're the reducing agent because you're letting someone else be reduced. If you are being reduced, you're called the oxidizing agent because you're letting someone else be oxidized. Okay? So the last thing we're going to do here is figure out how to assign what are called oxidation numbers when the charge is not obvious. When you have just ionic compounds, you know the charges, and you use those charges. But sometimes it's not quite that straightforward. So we use these things called oxidation numbers to help us take care and watch where electrons went, to see who lost electrons in a reaction and who gained electrons in a reaction, okay? It might look lengthy as far as what you have to memorize, but let's just boil it down and it's not too bad. Elements in their elemental form have an oxidation of 0. So that's kind of easy. Like if it's just plain iron, solid iron, or plain oxygen gas, those have oxidation numbers of 0. They're not charged. They're just in their elemental form. Okay, check. If you have an ion that's just a monoatomic ion, Fe+2, or Cl-1, then their oxidation number is the same as their charge. Okay, check. We get that, right? But if you have a more complicated compound, here's what you're going to do. You're going to go in this order. Oxygen is going to get the priority because he is almost always and forever -2. Okay? For us, I'm going to tell you oxygen is -2. Not if he's by himself, but if he's in a compound, his oxidation number is -2. There's one exception, which is peroxide, O2 -2, but we won't run into him. So oxygen has an oxidation number -2. Let him help you. The good thing about that is you're predicting him to be -2 anyways because he's on the periodic table in group 6. Hydrogen is kind of tricky, but not terrible. He can either be +1 like the group 1, or he can be -1 like group 7. You just see who he's bonded to. Almost always, if hydrogen's first in the compound, he's a +1. If he's not first, he's typically a -1. See who he's with. If he's with someone positive, he has to be negative. If he's with somebody negative, he has to be positive. Okay, so he can help you. Fluorine is always -1, so he's helpful. The other halogens, meaning other group 7, so chlorine, bromine, iodide, they like to be -1, but they don't have to be. So you don't always depend on them. And then the sum of the numbers have to equal the overall charge. So let's do a couple practices to make sense real quick. Okay? So if we look at H2SO4, let's go in order. Okay, we're not an element. We're not a normal metal, non-metal. So we got to deal with this group. Who are you going to depend on first? Oxygen. Oxygen's going to be a -2. There's 4 of him, so that's a -8. There's not a sulfur rule, so let's go to hydrogen. Hydrogen can either be +1 or -1. Do you notice that he's with sulfate? Sulfate has a -2 charge. So if he's with something negative, he is going to be positive. So he's a +1. There's 2 of him, so that's +2. Now, you see the whole thing's neutral? That means what is missing for sulfur here? I'll change my color so you can see. You need still a +6, right? So sulfur is going to be +6. So hydrogen has an oxidation number of +1 here. Oxygen has a -2 here, and sulfur a +6. Their totals add up to neutral because the overall compound is neutral. Is that clear? So these right here are the oxidation numbers. Let's try here. NO3 -1. There is a -1 there, so watch out for that. Oxygen's -2. Remember, we got to depend on oxygen. Times 3. That gives me a -6 charge. We need an overall -1 charge. So what does nitrogen need to be? We don't need to balance. We need to have a -1. So do you see that nitrogen is going to be +5? So right here are your oxidation numbers. Nitrogen is +5. Each oxygen is -2. Those are what you're looking for. Does that make sense? SF6. Okay, don't have an oxygen, don't have a hydrogen, but we have a fluorine, and he's -1. So -1 times 6, he's a -6, which means sulfur must be +6. So these are the numbers you're looking for. I could box them maybe. Does that make sense? H2S. Okay, hydrogen, remember when he comes first, he's almost always a +1. He's also with a sulfur who is generally negative charge, right? If he's not forced to be something else. So here, hydrogen's going to be a +1 times 2, which gives you a +2. So sulfur must be -2, which is fairly predictable for sulfur. But not always, because see how sulfur here has an oxidation number of +6. So hydrogen was our helper there. Okay? Here, let me give y'all the answers to these so you can work on them on your own, and then I'll show you the final kind of problems here. So carbon would be a +1 and oxygen a -2. So you can take your time, work through these, and see what you see that you get the same answers. Okay. So we're going to continue doing that, is why I'm skipping those. So here, now, let's use this. We're going to do these two problems for this video, and we'll be finished. Here, we're going to determine everybody's oxidation number, and then determine who is oxidized and who is reduced, okay? See how it asks for who's the oxidizing agent, who's the reducing agent. So we've got to apply all of our rules. Cadmium's all by himself, so he's a 0. Nickel 2 oxide, or nickel 4 oxide is actually what he's named. Who can you depend on? You can depend on oxygen. He's going to be a -2 times 2, so -4. And because he's a -4, nickel must be a +4. So right here are our oxidation numbers, +4 and -2. Okay. Water, who are you going to depend on first? Oxygen is the more trusty. Remember, he's always in -2. There's only one of him. So the hydrogens have to add up to +2. So each hydrogen is going to be a +1. Do you see what I'm saying? Oxygen's -2, so we need a total of +2. Each hydrogen +1. Okay, so far we have found these to be our oxidation numbers. Okay, now let's move to this guy. This can be a little bit trickier here when you have a polyatomic and everything going on. Okay, oxygen's the most trusty. He's going to be a -2, okay? There's a couple ways to think about this problem, but do you see how this is the hydroxide ion? Hydroxide overall has a -1 charge, so he has a -1 charge, which means is hydrogen going to be a -1 to give a -3, or is he going to be a +1? He's going to be a +1. Remember, hydrogen can only be +1 or -1, okay? So now let's kind of add here. There's 2 oxygens, so that's -4. There's 2 hydrogens, so that's +2. We need to overall be neutral here. So what are we lacking? We need a +2 to be neutral. See that? So cadmium is +2. That really could be boiled down to one of our normal transition metal problems where you're just determining cadmium's charge if hydroxide's -1. But this gives us each individual element. Okay, and then lastly, it's going to be the same situation. See how hydroxide's -1. So there's going to be a -2 and a +1 for oxygen and hydrogen. And there's still a 2, so nickel is going to be +2 also. Okay, you can work through that. It's the same math as cadmium had. Now, let's go see who did what and what changes occurred, okay? Okay, let's see. Cadmium was 0. What did he go to? He went from 0 to +2. Think on your number line. Did he go up the number line or did he go down the number line? He went up, right? So ask yourself, did he gain electrons? No. If he gained electrons, he would have gone down, 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 down. So he did not GER, he LEO'd, right? He went up the number line, he lost electrons and was oxidized. So I'm going to put LEO there so you see that cadmium was oxidized. Now nickel, let's focus on nickel for a second. Nickel went from +4 to +2. Okay, he's still in the positive world, but think about the number line. He's at +4. Did he go up or did he go down? He went down by 2, right? He went from +4 down to +2. So did he gain electrons? Yes. He didn't get all the way negative, but he went down, which means he gained some negatives. So he GER'd. He gained an electron, so he was reduced. Now, you tell me, who is the oxidizing agent and who's the reducing agent? It seems opposite, but just kind of remember that. Whoever's oxidized is called the reducing agent. So in this scenario, cadmium is the reducing agent, and nickel is the oxidizing agent. Because remember, they're allowing someone to be that, okay? So we have one more to work through here to practice. You can pause and try to work through it on your own would be my recommendation. And then I'll work it out right here as well. And you should only have 2 people end up changing, okay? There should be one who's oxidized and one who is reduced. So let's go find who those people are once you get to this point. So you'll notice everybody else that I did not talk about, they all stayed the same. Here we're seeing aluminum go from 0 to +4. So do your number line. Did he go up or did he go down? He went up. So he did not gain electrons, because if he gained electrons, he would have gone down the number line. So he must have lost electrons. So I'm going to write aluminum, Leo. He lost electrons. He was oxidized, which means he is called the reducing agent. See if that makes sense. He lost electrons, so he was oxidized. He's called the reducing agent. Then look at manganese. He's +7 and went down to +4. So since he went down the number line, he must have gained electrons, GER. So he gained electrons, he was reduced, which means he's called the oxidizing agent. Okay. In the filled-in notes, you may notice that there's an additional section on balancing half reactions. In this course, we don't cover that. If you take 152, you will look at that stuff. So if you notice a difference in our notes, that's why, and you can just skip over that. So there will be one final lecture for Chapter 4, and it'll start here with molarity.